welcome again to the final day of final presentations for astronomical observational techniques and instrumentations. The talk today is being given by Nguyen. We'll be talking about zodiacal light measurements with New Horizons.
Thank you, Dr. Feiger, for the introductions, and welcome everyone to my presentations. I will discuss how we try to do some test measurement using LORRI, one of the instruments on New Horizon. So this is how the talk will go. I will explain the motivations, namely the questions that we want to address with this project, a little bit background on the instrument and why we're using LORRI. I will explain what I did to reduce and analyze my data, and then discuss the current status of the project as well as what more can be done in the future. So our motivations is to answer the science questions, whether we can measure the extragalactic background light, EBL, with more precision if we are really, really far away from the sun. So it's actually really big questions, and this project will not be deep enough to answer these questions, since it requires deep knowledge of the instrument as well as the models of EBL and other sources that contribute to sky background. What I want to address with my project though is to test to see whether LORRI have the stability to measure the zodiacal light and distinguish it from the EBL. And I will explain how that contributes to this. So for those of you who don't know yet, the EBL that we are concerned with here is in the optical and the infrared wavelength. It's a combination of light from all of the stars and galaxies throughout the cosmic history. So it includes both light from local universe as well as redshifted light from galaxies and stars from really, really long time ago. So for stars and galaxies that were formed during the epoch of reionization, which is about redshift of 6 to 7, then the light, the wavelength that their light peaks in, are now redshifted into this regime. So if we study the fluctuations in EBL, we can distinguish which part of it is from local universe and which part is from the distant galaxies. And then we can give a really strong constraint on the stellar emission. More specifically, whichever models of star formation rate and distribution of galaxies like quiescent galaxies and starburst galaxies, etc. Whichever models that theorists can come up with cannot be more than the limit that we measure from EBL. However, it has been really difficult to measure EBL to high precision due to the bright fallout. And this is an equation that I want you all to keep in mind. Like, if you walk away from these presentations, at least remember this. So I will go back to that equations in great details in just a moment. This is to put the EBL in a big picture. This is a plot of the cosmic background radiation at multiple wavelengths. So at the millimeter. So on the low end, we have the cosmic microwave background. Everyone lies above it. We know it really well. At the far end, we have the UV and then high energy background. And there are surveys like the Fermi-Lat. They look at a lot of huge part of the sky, so they can also make the map of the background. In the middle, roughly about our distribution is where we are concerned with. And as you can see, we don't really know this part of the spectrum really well. And the reason is here. If you have a signal, it will have those extra terms in addition to the EBL. So if you break down your image in this unit, nanowatt per meter square per steradian, you will have contribution from the EBL, which is fairly isotropic. It's about 10. And then there's galactic light, which is the light scattered off from the intergalactic dust, the dust in the Milky Way plane. Its intensity is comparable to the EBL. However, this is not isotropic, and it depends on where you're looking in the galactic plane. So if you look into the plane, then you see more DGL. If you look like perpendicular to the plane from where you are, then you're gonna see less light. And then there's interactive starlight, which actually incorporates both stars, planets, local galaxies, basically individual stars that you can detect. This depends on where you're looking at on the sky. However, they are also manageable since you can just mask them out. Then there's the instrument, which depends on which instrument you're using. And then comes this monster, zodiacal light, which is really huge, which is very intense when you see them on Earth. So zodiacal light depends on also position things. So it also depends on where you're looking in the elliptic plane. At a length, you see that we are already dealing with a different coordinate system, and that will come into play later. So I will go a little bit deeper into zodiacal light. And what is zodiacal light? We have heard about this at many points during the semester. Is the light scattered off interplanetary dust. Previous measurement by some space missions like Pioneer 10 show that the intensity of the light is roughly a power law. It depends on the distance from the sun to where the light is measured. It goes by r to the negative 2.3. It's a little bit tilted from the elliptic plane. However, the general trend would be that the further away from the elliptic plane that you are looking, the less light from zodiacal light you should see. So at higher elliptic latitude, signal from this source should go down. There's also some time dependence, but I will not do with that for now. So if you have a lot of money and you can build a spacecraft, then we can go really far away from the sun, and we can point our instrument at a place where we are not, where our signal will not be dominated by zodiacal light. And luckily for us, we do have such spacecraft. So there's New Horizon. It made headlines a lot this year thanks to the Pluto flyby. It was launched 9 years ago and provides an excellent opportunity to observe things that are really far beyond the Pluto orbits. So it has quite a few instruments on board. They deal with different wavelength regime. There's also some ashes of Clyde Tombaugh, the guy who first observed Pluto. So he got to see his planet. The one instrument that we are interested in now will be LORRI. And why are we only interested in LORRI when there are also other things like RAF and laser not shown here? So they have some overlapping in their wavelength in the infrared, but we will use LORRI. And the reason is, I will explain in a few moments. So a brief overview of LORRI is a high resolution imager. It's a very small telescope, only about this big. It has no filter, and it observes throughout this whole wave range. It has a small field view, and it uses a 1K by 1K CCD. The CCD can also be used in a beam mode with like 4.4 pixel into just 1 pixel to increase the signal to noise ratio. The exposure time of its images is from 1 millisecond to 30 seconds. Now, this is a mechanical model of LORRI, just for completeness. There's the primary mirror, and then there's the secondary mirror. So one thing about LORRI design is that it doesn't have a shutter. So when it was launched, there's a door covering this part, but after the door is open, then it just stays open like that. So that does introduce some complications into the data later on. However, since we know what will happen, the team behind this instrument already have tests and algorithms to deal with that. Now, this is spectral response to show how the instrument works at different wavelength. There's this pivot wavelength. So at some point in my presentations, I will switch from talking about flux to flux intensity for some reason. And the flux intensity that I will report corresponds to this pivot wavelength. So why are we using LORRI and not other instrument? Well, it has the sensitivity that we need in order to get down to the level of precision where we can distinguish what we want to observe from the noise. So in 30 seconds, you can get down to 16. That is slightly higher than EBL. So instead of taking one image, you can take multiple images and combine the data together. For other instruments on board that have a comparable wavelength range with LORRI, you would need a lot more time to get down to that level of sensitivity. There's only one New Horizon, and there are a lot of astronomers, so we should go for the one that takes the least time, so that we can make a better side case. It also has really fine angular resolutions, so we can mask star better. We don't have to sacrifice a lot of extra pixels. What we don't know about though is how stable the instrument is. The scenario is this. LORRI was made to image things like planets and then the cubical objects. So those objects are a lot brighter than our object of interest, which is the EBL. So LORRI does really well when it looks at planets, but we don't know if we have a really faint source, whether the instrument will have fluctuations that is like on the same scale of signal or not. So we want to understand how the system performs when you have a really faint source. Now, the time of the images that LORRI have taken so far that are available to us doesn't have enough sensitivity to get down to the level that is comparable to the EBL. What it does have though is some information about zodiacal light. So as I said earlier, the further away you are from the sun, the lower the intensity of the flux from zodiacal light will drop. So at beyond Saturn orbit, zodiacal light should be faint enough that you can consider it like a low flux source. But it's not a source, so it's like diffuse. So what we can try to do is to see if we can extract other sources that are not zodiacal light and instrument noise. If we can plot that intensity versus the distance, if the result follow the trend of the power law that we saw earlier, then we know that, oh, this instrument is really good. Like its fluctuation is small, it's not not enough to confuse our signal. But if the plot shows some like a flat line or some like weird trend that doesn't correspond to how zodiacal lights behave, then we know that the signal is dominated by the instrument and not by zodiacal light. So that's the idea behind this project. And in the next like 10-15 minutes, I'll make this clearer. So we need data, and then we need to do something on the data. The tools that I use are written in MATLAB, IDL, GNU-plot. I use astrometry.net for detecting the field that we are looking at, and DS9 for visualizations. So I began this project like totally newbies in MATLAB, and I think now I can handle it so much better. So the data was acquired from NASA Planetary Data System. It comes in three phases: post-launch, Jupiter flyby and cruise. So the data is spread out and they cover a wide range of distance from to the sun. They comes into the data available to us two types. So there are raw data and then calibrated data. Due to time constraint, I just go with the calibrated data. And even then, there's still a lot of steps follow this that took a lot of time as well. So the calibrated data have been subtracted and flat-footed, which are pretty standard in standard procedures when you do photometry. The readouts mirror removal. Now this is where we go back to the shutter, the no shutter problem. So because there's no shutter, when the CCD is reading out, and I think it's read on both sides, there's still new light coming and hit the CCD. So you ended up with a straight out image like this. The people behind this instrument have algorithms where they can remove those artificial, like not useful data, and then we ended up with a much better image. So unfortunately, the data I have is not like that beautiful. And then the calibrated data is supposed to be converted to physical unit. The keyword is supposed to be because the documentations give very conflicting information on whether that happens or not. And that is also where I becomes really nervous to report my result in flux. So beside the confusions of whether that happens or not, there's also the fact that they report these things in really conflicting units. Like in some documents, they would use CGS and then mixed with nanometer, and then others like SI units mixed with angstrom, and a combination of the two. And sometimes like they're like different in precisions. So I will leave all of that outside the scope of this presentation. That is the work that I'm still working on. Instead, later on, my result will be reported in terms of the count value that each image gives me. So basically what my data have, I'll just show it to you. That also means that I have some loss in information that I need to deal with, but I hope that will be resolved. So I have a lot of data, like over 10 gigabytes of images, but many of them are just like 0.1 second of iterations. That basically doesn't give me a good signal to noise ratio. So I run a program through them to pick out only those with 9 to 10 second exposures and build to have higher signal to noise ratio. And then I run them through an astrometric pipeline that I wrote. Basically what it does is it extracts the RIN that is of the central pixel, and then it input it into a tool written by the people at astrometry.net. They have a library of stars, like a lot of few stars in the sky. So what they do is they will match the star in my image with the star in their library and match as many of them as possible to solve to see where are the sky that I'm looking at. If they have a nominal RIN deck to give the tools, then they can do that much faster since they have an idea of where to look initially. So that I run my data through it. It works really well for cruise data and for some of the Jupiter data. Didn't work at all for the post-launch data. So this is an example of the cruise phase image. The background looks really flat, but if you like turn up the contrast, then you see there are actually a lot of fluctuations in the background as well. Anyway, this is post-launch data. So this thing looks really artificial, and it appears in all of my data, all of the images of this phase. So I think this must be something from the instrument. I tried masking it, and then run the whole thing through the astrometric registration again. It still didn't work. And then I look at the number of sources that the astrometry.net tools detected, and I found a really huge number. But when I look at this image, I found that I don't see a lot of bright sources, and those things looks very suspicious. So one night I decided to make a movie of it, and then it clicked with me. Well, those images are taken on the same day, April 23rd. So it should be around like same field, but they were changing on the law. So, and then I realized, oh, that must be cosmic ray. So we are not looking at sky. We're not looking at like stars. And then there's also like this flash of light that happens at like almost the same period. So I decided to go back to the documents and look at the days that those images were taken to see if there was something weird going on, like was it passing in front of a planet or something, like, and well, as it turned out, the door wasn't open. So those images was the noise test, and that was taken when the door was closed. So I had a lot of 10-second iterations of anything but sky. And then what I did was I went back to the data and just look at those that come after when the door was open. So I know for sure that I'm actually looking at sky and not at the door. Unfortunately, there are no 9 to 10-second iterations during that period of the post-launch phase. So I had to reduce the threshold to just 1 second, and then choose the data, and now it run through astrometry.net tool again. Now it works. Well, so I have that. Now I have to find useful information from the chosen images and estimate the uncertainty. What I have are photometric data and a lot of records information on New Horizon and the targets. What I want is a plot of the flux or intensity versus the distance and the elliptic latitude. These are the steps that I have to go through to make it. The first one is getting information on the distance. That is easy because I just read it off from the image headers. So this is what I got. I can fit the trajectory fit through it just in case I need that information later. It's really easy. So for comparison, I plot the distance, the radius of orbits of some planets here. So we do have some before and some after shortened orbit. And this is just a sanity check to make sure that I'm not extracting the wrong data. I compare it with the non-distance from NASA website. And it says like I'm still doing okay. So then I have to look at the image. Remember earlier we had these combinations of sources in our image pixels. Now, since I said earlier, we don't expect that the test images that we have the sensitivity to actually distinguish EVL and diffuse galactic light from the noise. I will just cross these two terms out for now. So what I have left with are these 3 terms. So if I want to plot the combination of these two versus the distance, then I need to get rid of this, which is fairly easy. I just need to mask out those pixels which have intensity like outside of about 2 sigma of the median count. So to visualize it, this is a histogram of the pixel count, number of pixels versus intensity in each pixel. This is before and this is after I cut it. So I have to cut it, recompute the median and the standard deviation, and repeat it a few times to end it up with something that looks like Gaussians. So in terms of the real image, this is how it looks like. The white pixels are those with no data, so I just exclude their value from my image. And then, so this is, so now I'm left with only my 2 terms of interest. I can then compute the mean intensity by the standard deviation, the leftover pixels, which are pretty standard and easy to do. And then I can start plotting things, which is the interesting part. So if you just look at this part of the plot, fairly okay. There's some drop off at increasing R. It doesn't really seems like there's a strict power law fit over here. Like if you fit a line, they're going to be scattering. So we think that at least for this part, there are some. We may have some information from some detections of zodiacal light, but there are also fluctuations in system, in the instrument. But that is okay because that's what we're after. It's these three guys that make no sense to me. And that really make me like pull out my hairs and hit my head against the desk many times. I thought that maybe I didn't cut out enough stars, so I ran the star masking thing through them again and again and like increase the cutoff. But at some point I feel like I'm cutting out way too much data. I'm probably doing something wrong with it, and I still cannot bring them down to like compatible level with this. So, but then I remember, hey, I don't know the units of thing, so maybe, just maybe, my instrument wasn't looking like in the same elliptic latitude. So maybe during this time it was looking perpendicular to the elliptic plane, in which case I should get really little zodiacal light. And maybe during those time it was looking into the plane, in which case there may be more light. So I thought elliptic latitude versus mean intensity. It still doesn't make sense to me because what we expect to see is an increase toward zero. There may be a tilted a little bit, but the general trend should still be increasing towards zero. But there are still those outliers. So that was when I feel really bad and I feel okay, maybe our instrument is not doing, it's not suitable for what we wanted to do. But then last night when I was brushing my teeth, I suddenly realized that I still have one more plot that I haven't looked at, and it is this one. So remember earlier we crossed out the diffuse galactic light because we think that it wouldn't matter. But that term depends on where you're looking at in the galaxies. So when you plot the day of observation versus the galactic latitude and longitude, I noticed something. The day where the signals are really high are those when we look into the galactic center. So maybe my assumptions was wrong, and maybe that we should really consider this term when I handle my data. So what I have learned from this data set and what more can be done from now on? Well, I have learned that at least diffuse galactic light may matter for some points. Maybe it doesn't matter for all of them, but it doesn't hurt to actually consider them seriously. The data trend suggests that I may have some detections of zodiacal light. The scatter imply that the signal are still dominated by the instrument performance. So the conclusion so far now is that I need to better understand my system. And the bad thing is that since Lori doesn't have a shutter, we can no longer do any measurement on the current. On the other hand, I have a lot of 10-second iterations of when the door was closed. So maybe I can go back and see if I can find anything useful from those dark frames. So that's a thing to do more. Future work, well, the first immediately thing I need to do, which I'm gonna do after this presentation, is actually figure out the units of intensity and perhaps check with other people's work to see if my pipeline and my unit conversion is accurate. And then subtract diffuse galactic light where I should do that. And then just now trying to disentangle zodiacal light from the instrument component. Basically what I do is I will assume that we know how much zodiacal light we have and then subtract it from my data and see what's left. So in summary, EBL is still difficult to measure. Lori has some advantages, but since it wasn't designed to measure EBL, we have to actually check to make sure that it can do what we want it to do. Right now, measuring zodiacal light at multiple distance is one possible way to test to see whether lorry can achieve the stability at low flux level. And I still have a few more steps to finish, but I think now they are manageable after I realized the thing about the galactic center. So I really want to thank my advisor, mentor, who's unfortunately cannot be here tonight or today, since he helped me a lot with understanding the whole process. And yeah, this is the reference list for you guys to read. Thank you very much. I'll be happy to take questions.
Okay, questions? Excellent.
Do you know how they determined or derived that power law of contribution
So,
for the zodiacal light?
Okay. Pioneer took data also at multiple distance, and it was meant to do that. Like it actually like took those data deliberately and not like what we're doing. Like look at what we can see, whether we can accept it. So I think it does up to 10 AU, but I may be wrong. Like I had to go back to the paper to see, but basically it compute at different distance and it lies through.
Different distances within the same like latitude?
There are different elliptic latitude. That's
Okay.
why people know that it's tilted. I want to find if there's like more recent papers, but some of my references are really like old. Yeah, the newer one, some of them are in journals that I cannot access. Planetary people.
Other questions? I have a few questions.
Yes.
Go to slide 7.
This right?
Yeah, what would these numbers look like for sort of some representative sky positions? So like that 1,000, is that in the ecliptic plane? Pointing at the ecliptic plane, or is it?
I think that's probably it.
If it was orthogonal, what would that number be?
You mean like
Out of
out of plan? I cannot give you an immediate answers because I cannot remember the number on the plot, but like basically it starts with like and it's ish thing.
So I guess there's a sky map that
Yeah.
would correspond to each of these numbers, except the instrument, I guess.
Yes. So there are many groups who do this, and it's actually part of what they do to find EDL. So I think if you look at like plots from Derby and
Yeah, so I showed some in the course, and you could see the S curve.
Yeah.
So out of the plane, it's low.
So yeah, they know how much it is where they're pointing.
Okay. Go to 14. Why is there a sharp cutoff at 900 nanometers?
I think that's where is well, it's for design to work between 330 to 830 nanometer.
But from a physics point of view, why is there a cutoff there? What's this made out of? What material?
Let's see.
What kind of
What is
detector?
it?
What kind of detector is it?
It's not a Hawaiian. It's not a
It's a CCD, right?
yeah, it's a silicon.
So what are CCDs made out of?
Silicon.
Silicon. So what's the cutoff for silicon?
It's about like 48 micron-ish.
It's 1.1. So I'm wondering why there's a cutoff at 900.
I'm assuming that they're adding something to make sure that it like just the range that they want.
Maybe a long wave cutoff filter.
Maybe, yeah.
I saw something in the instrument. It had lenses, but I didn't see filters. But it could be,
Yeah, I remember it said that it doesn't give filter.
or it could be just very thin. So the long wave goes through.
So this is the thing I plot from the table, although they said that the test data doesn't really agree with this at long
What's the pivot wavelength?
So-
What does that mean?
This is something I'm trying to wrap my head around because I don't think it's the central wavelength of this spectral response. They have an equations for it, which involve like square root, which is also weird. So what they explain is that if in their raw data you will have your count will be in this unit and then per pixel, every pixel. What you can do to get a physical unit, those count will be to multiply by a conversion factor depending on the time source that you're looking at. Like if they give one number for stars and one number for planets, and that number is a flux intensity. So it will be per wavelength. So then in order to get this unit, you would need to multiply that by this pivot wavelength.
So usually pivot wavelength means it's the flux weighted wavelength when involved with the spectral energy distribution. So depending on the ICD, if it's like this or if it's like this, then the average wavelength is going to be different in such a broad band. It's just technically you should know the spectral energy distribution before
Yes.
knowing what the pivot wavelength is. So that's probably a typical number for expected ICDs.
Yes.
That's my guess.
Yeah, so I think so far in the documentation, they consider like few cases, like mostly those that align with New Horizon side missions, like planets, planet covering eyes,
Yeah.
stars. So what I thought is if I have the intensity and then if I have spectral response, maybe I can like try to do like recalculate it, like use this number and then use the spectrum to sort.
Yeah, so you can just reconvolve.
Yeah, so that's
Calculate.
what I want to do.
Can you monitor cosmic rays versus distance with the data that you have to see what the solar contribution is to the cosmic ray flux?
Like this,
Well,
or like this.
I mean, you have data at a range of distances from the sun. And so if someone were to ask you what fraction of cosmic rays, say at Earth, are contributed by the sun versus galactic cosmic rays, you now have a data set that you could look at that. I don't know if that's interesting. I presume that people have done that.
That's possible.
Right, also it must relate somewhat to the magnetic field, the heliopause of the sun.
Yeah, I think one of the purpose they did this test was to find how much cosmic ray was getting it. They had a number for that, so they do find the rate. So I still keep those that frames just in case anything.
Okay.
Was there a flare or something, or it was just normal, regular cosmic rays?
I think it's just cosmic rays in the door was closed. When I play video, you see some light flash. I think that was from their calibrated lamp. So they do have some light inside, so they can take like flat field when they are flying.
Go to 22. Oh, is that where you are? Yeah.
So yeah.
So you discussed this as sort of an unfortunate discovery, like you stumbled on this, finally
Yeah.
realized that this had the door closed, right? And so my question was, can you use these data and make some use out of them? And I think you already said you could use them maybe to infer the dark current
Maybe.
and also the read noise, perhaps.
Yeah. Actually, they use some of those for like taking the bias and
Yeah.
flat field. Right.
Go to 26. Did you make that figure in the lower right? You made it from the image.
This one?
The image metadata, right?
Yeah.
Okay.
Maybe different.
Go to 30. So why not take the mode as the best representation of the background?
That's an interesting question.
Because your tail on the right is, I think, due to sources, right? Extra sources. just took the average of the figure on the left, then your statistic would be skewed far to the right, just because of all those bins on the right,
Yes.
right? But you know all those bins have sources in them, right, in the pixels.
You mean like side?
Yeah, all those have sources, right, like stars, yeah. So,
Well, I mean, obviously I cannot take the main since we
yeah,
skewed.
right.
There's actually a lot like thing out there too from cosmic ray. So I'm just chilling long ingredient. Yeah.
If there are more pixels without sources than there are with sources, then you might consider taking the mode, because even on the right, I think a lot of those pixels are biased because they have sources in them, right? Because my guess is these pixels don't have sources in them, right? That's just a fluctuation around the mean. But these, I'm guessing, still have sources in them, so you might just consider the most frequent.
Yeah, I can try running that. I mean, for this one, it start with the options, but for the some of the pools like have a really crowded field. It seems like it still have like a little bit of a tail. But yeah. So yeah, I will try doing that again.
Do you happen to know how many electrons per second correspond to the zodiacal light? I guess that'll just fall out of the calibration you end up doing, right? Because it comes from relating the signal measured in the detector with the background. So maybe you're not at that.
I'm not.
Okay. Okay, that's all I had. Any more questions? Okay, let's thank Chi again.